there are challenges here. And this is kind of the main challenge that I'll talk about a bit later today, is that we cannot afford to do retraining for sort of all of these models. For instance, the standard sort of training cycle for these models would require between, I don't know, 400 and more than 1,000 GPUs for about 2 weeks, which would take around 3.2 million in a very optimistic terms, assuming you can actually get that many GPUs these days. And then you also need a very high degree of accuracy for your compression, because in order to generate the same or a similar sequence of predictions as the original model, you would need to exactly or close to exactly match the model's output distribution. Okay, and by this kind of 3.2 million for compression, I mean per run, so excluding the cost of hyperparameter tuning and so on. Okay, so in this talk, I'll try to give you some kind of high-level algorithmic results and sort of accuracy results, but Mark will also talk later about actual sort of real-world results that you can achieve using our software. So what the good news here is that we can compress such models, including the GPT, OPT, sort of quality and size type of models by more than one order of magnitude with minor impact on their accuracy. This is a good idea in terms of deployment. So using Neural Magic's custom implementation, you can obtain more than 6x speedups on CPU. So you can actually run more than you can run sort of several tokens per second. And then there's my side of the story is going to be that to convince you that there's some nice sort of math behind the compression that is quite general. So it works for pretty much every model. And then you'll also see from Mark that it all comes together with some pretty impressive graphs. And this is pretty easy to use overall. Okay. So like from my side of the world, we're giving these very large models. But this isn't all that different from sort of any compression problem. So we essentially, we have one of these large models, and we essentially want to find a sparse or quantized subnetwork, let's say, such that the loss of this subnetwork is approximately the same as the original loss of the model. Okay, so given sort of a fully dense, extremely large network, we essentially would like to find a subnet which best approximates its behavior, which has as few connections on as possible, but at the same time, maybe the sort of bit width of those connections is minimized. There's been a tremendous amount of research interest in this problem. So there's been more than 300 research papers and several research waves over the last few years. However, the interesting thing about this problem from the conceptual side is that we kind of already know, I mean, the optimal answer can be determined. It's just very, very hard to sort of implement in practice. So what do I mean by this? So I'll at this point, I'll take a brief detour and things are going to get a bit mathematical, but don't worry, we're going to come back to sort of real world implementations soon. So what I mean by the mathematics of compression is that conceptually, given a set of trained weights W, pruning or compression is just a specific way of perturbing the weights, okay? So applying this perturbation delta W to our weights W. So assuming that this perturbation is small, we can actually write Taylor's expansion of the loss around the point W and obtain this formula here. Given that our model is usually well optimized, the second term can be dropped. So in particular, this means that the difference in loss between the original model and the perturbed compressed model should actually be minimized when this term, second term, is minimized, okay? So essentially, we need to solve for this form of the perturbation, which would minimize this term here. So what's very interesting is that this problem can be solved exactly. So in order to find out the weight that should be pruned to minimize the sort of impact on the loss, we can actually obtain these formulas where essentially the weight of minimal impact on the loss would be the weight which minimizes W, like the size of the weight divided by the Hessian inverse corresponding to that weight. And then the optimal perturbation, which sort of fixes the other weights with respect to the removal of this one, has this formula here. It's not so important to understand the sort of specifics of what these terms mean, but just to understand that we can rank the weights in a very specific way, and that this formula depends on being able to compute the second order derivative of the model at the current point. And to verify that our math is correct, we can actually replace this this kind of second order derivative by the identity, and we just obtain the fact that the kind of optimal weight to remove, assuming this very coarse approximation, would be the weight of minimal weight. So we obtain essentially magnitude pruning if we're willing to assume that the Hessian is the identity, which means that our weights would be kind of uncorrelated. Okay, so that's sort of a bit of math, but there's kind of this inherent tension between the fact that we know these formulas, they exist. However, to implement them as the size of deep networks is practically impossible. And this is because this matrix essentially has dimensionality d squared, where d is the dimension of our model. So for a ResNet 50 model, which has around 24 million parameters, the size of the matrix would be around 5 petabytes. Okay, so we can't even store this on any reasonable system, let alone invert or compute with it. Okay, so the problem here is that one cannot simply compute this, and therefore we cannot compute, we cannot sort of determine the optimal compression for a neural net. So instead, our approach, which we have implemented in Neural Magic Sparse ML and has been sort of developed over a series of papers which appeared in consecutive years at NeurIPS, is kind of an algorithmic toolbox for approximating sort of the curvature information encapsulated into this Hessian matrix for estimating essentially the curvature or Hessian for deep nets. And we're able, with algorithms that are implemented in sparse ML, to sort of do this and with respect to blockwise approximations of the Hessian or layer-wise approximations of the Hessian, or actually sort of do global approximations of the Hessian in reasonable linear time in the number of parameters. So what's interesting is that you might wonder, why don't we just use one of these, in particular the global approximation? Well, it turns out that different levels of granularity seem to be necessary for compressing different model types. So for instance, a CNN might actually benefit from a different type of approximation than a transformer, okay? And then you can actually try it for yourself using deep sparse. So you'll see that these implementations can be very fast and accurate, and like you can compress pretty much any model in a couple of hours if you have a GPU, okay? So, all right, so what is so special about compressing GPT models? Well, the key issue here, which I mentioned before, is that we cannot train. So standard methods are known to benefit, standard methods such as the one I just enumerated benefit from taking model gradients. So for instance, to take the model curvature, we need to estimate the Fisher matrix. And we can also benefit from the fact that we can fine-tune or retrain our model slightly in between the compression steps to sort of adjust its output behavior. However, we're kind of in the nasty situation where the models, like these GPT scale models, are literally 1,000 times larger than the ResNets we're kind of used to be compressing. And therefore, taking gradients is actually too expensive. So we need to compress in some sense in a single step without being able to do any retraining. Okay, and for this reason, before our work, there was no kind of non-trivial pruning methods at GPT scale. And then just sorting the weights and selecting them by magnitude pruning will crash after a trivial amount of sparsity, less than 25% has been imposed, okay? There's been a lot of work emerging on quantizing such models, but there's much less work on pruning. So how does it actually work? So basically what our method does is it instantiates the, it tries to instantiate this kind of second order approach, but in a simplified setup which will allow us to do this efficiently. So basically we're going to take the original network and we're going to break it into layers, okay? And then we're going to solve some problems at every layer, assuming that we have run a subset of data S through the layers, which will allow us to get sample inputs and outputs for every layer, okay? And then for every layer matrix W, we'll get sort of a subproblem of the following form. We would like to minimize the L2 distance between the outputs of this layer before compression and its outputs after compression, where this sort of WI hat just means that the matrix has either been sparsified or quantized, okay? And then the thing is like this has simplified our problem because we have been able to break it into smaller ones, but this problem is still going to be NP hard for sparsity or quantization constraints. So, however, the hope is that if we solve each individual subproblem with low enough error, we could actually stitch back together the quantized weights and or pruned weights, and we can still obtain a reasonable model. Okay, and then our approach, which appeared in a paper with my student Elias Frantar, I'm going to show you the version for quantization here, is basically as follows. So we essentially go back to the formulas by Lecan that we have just discussed before, and I'm going to instantiate the version of this for quantization, where I just replaced Wi from before with Wi minus this quantized value. So we're going to obtain these fancy second order formulas, where this gives us the optimal order of weight quantization or weight pruning, and the second update formula essentially tells us how the other weights should be updated once we have quantized or updated a specific weight. Okay. Now, doing sort of pruning or quantization of a model that's 175 billion parameters, one weight at a time, will take a very long time, as you can imagine. So we're actually going to do a version of block quantization. So we're actually going to quantize large blocks of weights in one go. So this formula is not very useful. However, the optimal update still turns out to be very useful because it will allow the mass set of weights that are still available to sort of compensate for error that's kind of due to quantization. Okay, so that's kind of the intuition. However, to realize this intuition, we would again need to estimate this quantity here, which we cannot do in kind of any reasonable form, since we cannot actually even take gradients for this model. However, there is a trick here, and for which I credit kind of my student Elias Trantar. So the trick here is that, remember, we have been minimizing the layer-wise L2 loss, okay? And the trick about the L2 loss is if you can differentiate it twice, you're going to obtain a constant Hessian. Therefore, by which I mean that the weights and the inputs are the Hessian is independent from the weights. It only depends on the layer inputs. Okay, so since it is constant, it can be actually pre-computed for every layer, and we can actually use it at the beginning of the quantization or compression process. And then we take advantage of this as follows. So the algorithm will just take the weight matrix, and then we'll go over columns, which I will call J. And then at column J, what I will do is we quantize or prune the values in column J, and then we update always to the right, following kind of the optimal formula that Lecan gave us. Okay, and then once we are done, once we're back at the last column, where we essentially call it a day, and we're done quantized. Okay. And then there are a couple of tricks here. One, that all the row-wise Hessians stay always the same, so the process can be implemented efficiently and in a stable manner. And then the asymptotic runtime of this is actually very fast. So I can maybe discuss this more in the Q&A if people are kind of interested. But basically, here's what you get when you implement this procedure. So basically, we're going to look at accuracy versus the bit width of a remaining model. And then if we look at the OPT model family, what we see is that standard round to nearest quantization, which has been used by previous methods, essentially will start to explode every now and then, just because it's kind of not able to preserve the accuracy of the model. However, we noticed that our method, which is called GPTQ, is actually able to closely track the FP16 performance. In particular, we have negligible compression loss for the very largest models, 66 billion and 175 billion depicted here. The same thing happens for the Bloom model family. And in fact, we can go to 3-bit weights without very significant accuracy loss. Okay, so this is good news because we can compress models by pretty much what I promised initially, 3 to 4 bits per weight, and still maintain Pareto front, by which I mean sort of the compressed larger model is still much better than the original, than the sort of smallest model to its left. Okay, and on the other hand, one thing that's kind of really nice with deep sparse is that we can combine sparsity and quantization, and therefore we can essentially apply kind of combinations of sparsity, let's say 50% sparsity plus 4-bit compression of the remaining weights, and we're still able to kind of do better than if we only did quantization. So to give you a simple example, this would be sort of the baseline dense, and then this is what happens if you have 50% plus 4-bit, and then this is what you would get using our method if you go direct to 3-bit. So it seems like sparsity gives you a sort of a boost in terms of flexibility, in terms of the way you would compress your model. Okay, so at least from this point of view, these results seem promising. So at this point, I'll maybe switch over to Mark, who can actually show you some real world implications of these results.
Awesome, thanks, Tim. All right, and I think I need you to stop sharing because it doesn't want to let me share yet.
All right, let me see how to do that.
Perfect. All right, hi everyone. So yeah, let's dive into what this actually looks like when we start trying to exploit all of the mathematics and algorithms that Dan just walked through, and specifically exploiting that with deep sparse. So deep sparse is an inference runtime that we offer that achieves GPU class performance on CPUs. It's targeted at x86 CPUs, meaning Intel, AMD servers, laptops, desktops, things like that. Usually probably what most of you are watching on right now. We do have an ARM beta that's going to be launching soon with our 1.6 release. If you're interested in that and signing up for the waitlist, definitely go here. We want as many testers on that as possible, and very excited to be launching ARM, especially as we look at LLMs and other large models, so we can compress these and deploy them right next to where they're needed. All of this is developed by our high-performance computing engineers to achieve the best CPU performance for neural networks. And we'll talk over how we compare CPU versus CPU even without any optimizations, as well as what that looks like to be able to optimize those, both by utilizing sparsity and by utilizing something that we call tensor columns to outperform GPUs. Specifically, what we're doing is we're using the caches in a very unique way on the CPUs, so you can get really fast memory access and much faster than what GPUs can even get in some cases. And the other big thing, and the reason why we want to have this webinar, aside from all the algorithms, is that we've now been able to include something called KV caching into deep sparse. We'll be releasing all of that soon, but just to walk through it a little bit, essentially what it's going to do is reuse previously seen tokens within the LLM so that we can significantly reduce compute. Right, as we're generating tokens, we're constantly keeping all the tokens that we just ran, and then adding one more as we continually inference this model to generate the text, right? So an autoregressive way of formulating the problem. What that leads to, though, is a lot of repeated computation, and there are a lot of implementations around KV caching that support this to essentially reuse that compute, so we don't have to rerun it at all. We've been able to improve on that and include it natively in deep sparse so that we can get significant performance speedups as we'll show. And so diving into those performance speedups with software beats hardware. So utilizing Sparse GPT and deep sparse on just a 4-core CPU, right? So again, going back to what most people are probably watching this on, you have more than enough power, most likely, in your current computer to run and get the numbers that we're about to show. So we show a 6x speed up on CPUs as compared to Onyx runtime. And not only that, but we're able to get to equivalent to a GPU as compared on a T4. So let's look at what that looks like. For an OPT 1.3 billion parameter model, right, that's been sparsified and quantized, deep sparse is able to get to 37 tokens per second. So every second, we're able to generate those 37 new tokens as we're running through. T4 GPU gets to about 39. And then Onyx runtime 4-core CPU, even with its KV cache implementation, is only able to get to 7. And diving into that a little bit more, so what happens when we increase the model sizes, right? Well, our speed up on CPUs stays the same, and GPUs run out of memory. So at least on the T4 that we were running on, obviously you can get larger GPUs, but you're going to end up with this issue, and the one that Dan highlighted before, which is that GPUs have very limited memory, and CPUs, you can easily throw a terabyte of memory on these, and it's a very memory-bound problem. So provided you have enough memory, you don't need these large clusters of GPUs to actually run these. So looking at this for a 2.7 billion and 6.7 billion OPT model, both of these cannot run on a T4 without significant improvements to essentially offload a lot of the storage to CPU when running on that T4. But when we look at this for 2.7 billion on a 4-core CPU, we're able to get to about 20 generated tokens per second. And then for 6.7 billion, we're able to get to 11.2, right? And as those model sizes increase, the perplexity decreases, and therefore it becomes a little bit more useful and also more accurate in what it's generating. So let's talk over what that looks like then, and how we've been able to essentially transform the Pareto frontier, something we've been pushing for a long time with sparsity and quantization, right? So this increase in performance not only matches traditional GPU deployments, it shifts that performance versus accuracy curve for LLMs. So an OPT 6.7 billion model that's sparse quantized is faster and more accurate than an OPT 1.3 billion baseline. So let's look at what this looks like. Here we have our Onyx runtime running dense. Then we have our deep sparse running dense and our sparse quantized in deep sparse, right? And what this is showing is on our left, we have perplexity, lower is better, and generated tokens per second on our x-axis where higher is better. So we're going to see the 6.7 billion, each of these dots is one of the models. So 6.7 billion, 2.7 billion, 1.3 billion, and 350 million. So let's look at just the 6.7 billion. Here we can compare to the Onyx runtime baseline, where we're barely generating any tokens per second. Just running that in deep sparse, we immediately get a large bump, right? And then going all the way to utilizing the sparse GPT algorithms, where we can create a sparse quantized version of this model with roughly the same perplexity, but with significantly more performance, right? And we're able to get above 10 generated tokens per second. And again, this is only on a 4-core CPU. And what that means is if we look at it as compared to our dense Onyx runtime baseline, which is our 1.3 billion right here, or even just the dense baseline in deep sparse, which is 1.3 billion, we can see that not only are we more accurate with our 6.7 billion model, but the sparse quantized version is even faster than both of those. So now, whenever we have our inference constraints set up, say that we need to generate 10 tokens per second so that the user doesn't leave the app, or whatever your constraints might be, or maybe you want to run more streams, things like that. Ultimately, this means you can deploy a larger model and a more accurate model, but keep the exact same performance or better. Now let's talk over what this looks like to run. So all the sparsified LLMs, we will be pushing to our open source Sparsu within the next few weeks. And the deep sparse generative pipelines will be released with 1.6 and in the deep sparse nightly within the next few weeks. Looking at what the code actually looks like under the hood, it's as simple as from deep sparse, import our pipeline. We're going to create our pipeline, and then we're going to run, let's say, what's the best city to travel to through that and get our response. And it's as simple as that. Currently, we have support for Linux and, as I said, x86, and we're working on getting Mac support as well as ARM support. So you'll be able to run these on your MacBook just as easily. Now let's talk over enabling anyone to sparsify. So Sparsify, it's an ML model optimization platform to accelerate inferencing at scale. And we're going to be pushing out our alpha version of that shortly. So let us know if you'd like to participate by scanning the QR code, which we'll show in a minute. It enables anyone to automatically sparsify their deep learning models in a few different ways. So one shot, no retraining necessary. You can increase your performance in minutes. And this, the sparse GPT algorithms all classify under this one shot work. Sparse transfer, you can utilize our Sparsu to transfer a sparse foundational model onto your data set. So we have a lot of models pushed up there, whether it's in LLMs or in other domains like object detection, image classification, NLP, things like that. There are a lot of models up there that'll work for your data sets. And then training aware. So you can utilize our state-of-the-art algorithms to compress your own custom model. And the beta version will support generic implementations of exactly what we have in this presentation for any LLM. And it will be as simple as sparsify.login, use your token that you get from our cloud, and then sparsify.run one shot, pass in the path to your model, pass in some calibration data. The nice thing about this is that it will all run locally on your machine, so we never see your data. And then we have the model ready to go so that we will show you what the performance looks like, how you can improve it, and not only that, but also what your accuracy is going to look like. So please join our early access waitlist if you're interested. Go ahead and scan that code, and I'll wait for a few seconds on that. But definitely looking for as many people as we can to come in and trial the Sparsify product that we're pushing out. So again, just trying to make it as easy as possible for anyone to do exactly what we just went through in this presentation. So what's next? Well, first, we're going to be pushing more LLMs into the sparse soup. So specifically pre-sparsified LLMs, so both pruned and quantized and so ultimately compressed for both community and commercial use cases. Ones that we're targeting next include CodeGen and Bloom, but more importantly, looking at the popularity of chat models, we have Red Pajama, Stable LM, and MPT. These are all open source chat LLMs that have come out in the last few weeks that are already on our pipeline that we're going to begin applying Spark GPT to, so we can push these out so anyone will be able to deploy large, accurate models on their own devices. Then for Sparsify, so cloud service to apply sparsification to all of your models, as we just talked through, be able to take your model, run the one shot, and then you'll get your own sparse model. So if you don't want any of these or you have your own fine-tuned one, you'll be able to utilize that and push that out. And then deep sparse, drive performance across models on any hardware, right? So edge to cloud, ARM, AMD, Intel, working on across all CPU vendors. And then running through what we're looking at for the research, we're looking at achieving higher sparsities with OBC. Currently, all of the results that we showed were for 50% sparse models. And then additionally, higher sparsities with training. Right, so we already have some early research that shows after applying the OBC algorithm, so after pruning that model, with the lower size models, we do see a little bit of an accuracy degradation, but training for only 2% longer or so, after we've applied that one shot, actually fully recovers the accuracy for those models. So we'll be looking into that and also pushing sparsity significantly higher, ultimately targeting 80 to 90% on these LLMs. Additionally, lower bit quantization. So currently all of the results that we showed here were at int8. As Dan highlighted, the algorithm can go down to int4, int3, and even further. So we're going to be productizing the int4 pieces next to get, hopefully, we're looking at 2x speed up over the top of the int8 that we have currently. And additionally, pushing that to lower levels down to int2. And finally, improved engine performance. So this is just the start of us getting into LLMs and trying to get the best performance that we can. There are a lot of improvements that we're going to be including to achieve even further performance. And again, just highlighting that everything will be continually pushed into our community-focused repos and products. So just highlighting those one more time: Deep Sparse, SparseML, SparseSoup, and Sparsify, which is coming soon. So hopefully everybody enjoyed that talk. And we'll open it up for questions now. All right, and just running through some questions that we have right now. One came in about the ARM beta, are M1 Max interesting? So yes, this is definitely something that we are actively looking into right now on if we can get everything working on the M1 Max. We have quite a few people and even on our team that have the M1 or M2. I personally do, and it is extremely annoying right now not to be able to run a lot of stuff on it. So yes, we are definitely targeting M1 and M2 Max with ARM support there. We have another question. Do you think this gives us insights into precision required during training? Could there be future hardware that supports training models at say int4. So there's some, and Dan, I'll pass it off to you in a second, but there are some really interesting papers that have started coming out that are trying to leverage lower bit training for specifically for LLMs. Most of them are freezing the weights at some point, so you fully converge that model, go through quantization, then freeze those weights. Then you can add another head or something like that onto the LLM and focus training on that. Dan, I don't know if you know of anything that does end-to-end int4 or int8.
No, I mean, certainly not for this size of model. I think there were some kind of demos like a long time ago, in fact, for 4-bit training for a specific, very, very specific models. But I don't think this is achievable right now without our accuracy degradation.
Another question coming in, will your demo models also include a one-click exe install? And it's a great question. Everything that we have pushed up for these libraries is pip installable. So as long as you have Python on your system, you'll be able to just go in pip install deep sparse, pip install sparsify, pip install sparseml, and so on, and it'll be available and at your fingertips. So you don't even have to install an exe to be able to utilize all of these. We had another question coming in. What is the token per second rate of GPT 3.5 Turbo and GPT-4 on their GPU hardware? Maybe Michael, I don't know if you know these.
I don't think those are public.
Yeah, they definitely don't push them public. I know there's been some tries at estimation, but I don't know the latest state on that.
Yeah, I think it would be disingenuous to guess. I think, you can measure by using the API, but who knows how many GPUs they're using or what the size of the models are. So it's kind of, that's what you get with, closed API.
Then we have another question coming in. Does this support sentence transformers? We do have some early work that we've done on sentence transformers, and we're going to be pushing up. Actually, I think I'm trying to double check in my head if we have those pushed up to our sparse-2 currently. We had some early work that I need to double check if we do or not. But yeah, all of the algorithms that we ran through definitely can be supported on sentence transformers, and it's something that we're actively interested in and have quite a few questions both from community and commercial to support. So it's something on our roadmap towards the future. All right, another one coming in. Dan, I think you'll like this one because we talked about it before. Are there any other metrics besides perplexity being used to assess quality of LLMs?
Yeah, so I mean, there's quite a few metrics and quite a few different evals. So basically, we've shown mainly perplexity. What you can find if you have a look at the papers is also zero shot, sort of accuracy for a very wide range of tasks. Like for instance, there's this big bench set up, and like there's some kind of evals from stability. So my point is that we have conducted kind of cross tests with respect to perplexity loss versus loss of accuracy in zero shot, and we have noticed that these correlate almost perfectly, with more noise in the zero shot, like in performance over zero shot tasks, where sometimes the quantized model will actually do significantly better than the dense one without a reasonable explanation. So to sort of answer the question in short, we have we have examined other metrics, but they seem to be pretty much saying the same thing. Like the perplexity correlates very, very well with zero shot accuracy.
And then Michael, I think you can probably take this one. What are RAM requirements for running popular LLMs on consumer CPUs? So mentioned Bloom and Red Pajama.
Yeah, so I think it's actually really transparent in terms of just look at the size of the model on disk, and that's exactly what we're working on in terms of the compression methods. So right, and talking about reducing the precision of the model from say like the original FP32 or FP16 weights to int8, int4, 2-bit, and then also introducing sparsity as another thing. And from there, what we're working on in the engine to make it as both performant, where the performance comes from memory movement and movement out of cache on this LLM workload, is representing the weights, the sparse weights in a compressed format. So you don't need to allocate as much memory or move as much memory. So I would think you can be, it's pretty easy to do back of the napkin math of the precision and the sparsity you're able to get, and that's a good estimate for how much RAM is needed. And we're working on making that as close to the napkin math as possible.
Yeah, so Michael, maybe you can give an example for like the 1.3 billion model. Do you know roughly how much we were looking at for that one?
Yeah, sure. So for int A50, sorry, I need to look on disk in order to remember the size of that model.
I think that should be around 4 or 5 gigabytes in FP32.
Yeah. So I think roughly 2 gigabytes for a sparse quantized, 50% sparse quantized model. I think we can do a little bit better than that as we move on. Maybe at least 4 gigabytes to be safe.
All right. And then based on your expertise and experiences, is it possible to get an 80 to 90% sparsity on a 4-bit 7 billion parameter model? Dan, maybe you want to dive in on this one.
At least right now, what we're able to get to is like without significant losses, something like 50 to 60% sparsity with 4-bit. But I think with fine tuning, we should be able to easily reach 80%, I would say.
All right. And then there's a follow-up on the earlier question on OpenAI's generation token rate. And just saying that calling out, trying to compare as treating OpenAI as the market leader and seeing that as being our ultimate goal. The one thing I wanted to call out is that while we're, obviously OpenAI is competing in the LLM space, there are a lot of open source plays that are as well. And ultimately what we're trying to do is enable it so that people don't have to go to these large APIs where they may have data concerns or latency concerns and things like that, and they can deploy right next to their users. So while we are a little bit in competition with all of this on OpenAI, or with OpenAI, the bigger thing here is just being able to enable anyone to run locally, right? So it doesn't meet the criteria both for accuracy and performance on your deployment, and if it does, then we enabled what our target was there. Then we had another question: when do you expect the LLMs to be available in the sparse zoo? So we're actively working on that right now. We expect to be able to have that up in roughly the next few weeks for the current ones that we just showed, and we'll be quickly following up after that with more models. As I said, CodeGen, Bloom, the MPT, Red Pajama, chat-based models as well. Timelines on those are a little rough right now. CodeGen we're actively working on. We expect that one to be coming out in a few weeks as well. The Red Pajama and MPT likely going to be a month or more out right now, mainly just because we're spinning up on research on it currently. All right, and then let's see. Also, is Neural Magic an open source project and looking for active contributions? So yeah, great question. Quite a few of our code bases are open source. The pieces that are not are one, deep sparse, which is the active, or at least the engine behind deep sparse. There are a lot of pipelines that we have open source that are on top of deep sparse. So definitely looking for contributions there. If there's any place that you think deep sparse would integrate well with for deployment pipeline, definitely feel free to push that up. We have a few active contributors right now that are external from the company, and always looking for more for whatever people are working on. And the same thing goes for the SparseML side. SparseML is completely open source, so all those research and productized algorithms are all available. And yeah, if you're interested in contributing there, then would love to have you on. All right. And I think that's it. We'll just give it one more minute for any other questions that might come in. But if we don't have any more, thank you everyone for listening in, and really appreciate everyone that signed on. All right, I think we're good to go. Sasha, was there anything that you wanted to sign off with?
Thank you very much, everyone, for coming, and thank you, Dan and Mark, and of course, Michael, for answering all the questions. We hope to see you in our next webinar. Please go to neuralmagic.com to see what's up next in our schedule. See you guys.
Take care.